Drop two objects and watch one defy physics, as we reveal 3 ways science class lied to you about gravity. What I'm about to show you changes everything most people believe about this fundamental force. Did you know that the shape of an object affects how it falls? This isn't just a theoretical quirk, it has real-world implications. For example, consider a tennis ball and a solid metal sphere of the same size. They will fall at different rates due to air resistance. By the end of this video, you'll know the exact reason 9 out of 10 people get this completely wrong, and how to fix it in under a day. Most people think they understand why objects fall at the same speed, but these hidden variables will shock you. And it starts with a detail almost everyone gets wrong. Wait, that's insane. If all empty space in your atoms was removed, the entire human race fits in a sugar cube. This might seem like a strange fact, but it actually highlights just how much space exists within an atom. The vast majority of an atom is empty space, which makes up for the tiny mass and size of its nucleus. So when objects fall, their actual interaction with air can significantly alter their descent rate, even if they're supposedly in freefall. But here's the part that breaks your brain. Imagine you have a feather and a lead ball drop from the same height in a vacuum chamber. In this scenario, both would hit the ground at exactly the same time, as predicted by Einstein's theory of gravity. But outside the vacuum, air resistance complicates things. The feather experiences more drag per unit mass compared to the dense lead ball, causing it to fall slower. This is why, in everyday scenarios, we often see feathers falling differently than heavy objects. And what scientists found when they looked even deeper changed the whole theory. That's coming next. If you've ever tried to drop objects from a height, you know the thrill of watching them fall. But what if something didn't behave as expected? And what if that one time you saw something defy gravity taught you more than your science class ever did? Here's the part that's going to make you rethink everything you thought you knew. Most people never realize how much this quietly cost them in wasted effort and confusion. Imagine spending years of your life, maybe even decades, thinking you understand basic physics, only for one little test to show you just how wrong you were all along. And the worst part, this isn't some obscure lab experiment. It's a drop test most people have seen countless times but never truly understood. Let me give you an example. Picture this, dropping two objects of different masses from the same height. Most physics classes teach that they hit the ground at the same time, but what if one object was dropped from a slightly higher point or had a small initial velocity? You'd see it land first, which could make you question your understanding of acceleration due to gravity. This isn't just an abstract concept. Think about how this misconception might affect everyday situations, like judging distances when dropping objects, or even in sports where timing and trajectory are crucial. And the truth is, your science class lied to you about gravity in 3 ways that could be messing with your understanding of how things actually work. First, they taught you that air resistance doesn't matter much, but it can significantly affect lighter objects, altering their fall time. Second, they probably didn't emphasize that gravitational acceleration changes slightly depending on altitude, which means your standard textbook formulas might not always apply accurately in real-world scenarios. Lastly, they might have glossed over the fact that gravity isn't constant. Its strength varies due to factors like proximity to massive objects or even different geological compositions of the Earth's surface. Now, most people stop here, but that's exactly the mistake. Let's take a simple example, stepping on an elevator. When it suddenly accelerates, you feel heavier. Did gravity increase? No. Your feet are simply exerting more force against the floor due to the elevator's acceleration. This is why scientists say gravity changes based on velocity, not just location. Here's another surprising one, standing on a hilltop. You might think gravity feels stronger at higher altitudes because you're closer to the center of the Earth, but that's wrong. Gravity actually weakens as you move away from the surface. The closer you're to sea level, the stronger it feels. For instance, if you stand 10 meters above sea level, the gravitational pull is about 42% weaker than at sea level. That might not sound like much, but it's the concrete detail that shows gravity isn't as straightforward as we think. So why does this happen? It's all due to how mass and distance affect each other. According to Newton's law of universal gravitation, the force between two masses is proportional to the product of their masses and inversely proportional to the square of the distance between them. This means that even though you're closer to the center of the Earth at a higher altitude, the additional distance from the surface makes the gravitational pull weaker. What I show you next is the part that sticks. Imagine you're on top of a mountain 100 meters high. The radius of the Earth is approximately 6,371 kilometers, so your distance to the center increases by just over 0.02%, which results in a noticeable drop in gravitational force. This small but significant difference can be measured and explained by these hidden variables. And what scientists found when they look even deeper changed the whole theory. That's coming next. Here's what the evidence actually shows, and it contradicts what you've heard. In your science class, gravity was taught as a simple force. But here's the mechanism almost everyone misses. Quantum fluctuations in space-time are constantly pushing and pulling on falling objects. It's like every atom in an object is having tiny tug-of-war with everything around it. And this isn't just theory. It's been observed in particle accelerators, where particles behave erratically due to these quantum effects. Imagine if you dropped a feather and a bowling ball from the same height. They should hit the ground at the same time, but quantum fluctuations might make one fall slightly faster or slower than expected. This is why scientists now use highly sensitive instruments to measure gravity's quantum aspects in controlled experiments. Stay with me, the next part changes how you see this. Now here's a part most people completely overlook. In every science class, you learn about Newton's laws of motion and the basics of gravity. But have you ever considered this? The way we measure weight is actually flawed. It's based on a misunderstanding of what gravity really does. Picture a seesaw at a playground. One end goes down when the other goes up. Now imagine if someone told you that seeing both ends go down was normal. That's how people think about objects in freefall. They should be going down together, but they don't. The difference is subtle but crucial. So why do we teach it this way? It makes gravity seem more complex than it needs to be. If you're curious and want to learn more about these hidden truths of science, subscribe now for new videos every week that peel back layers unseen in class. The universe has operated this way for 13.8 billion years. We only discovered it recently. What else are we still completely wrong about? Here's the thing nobody actually talks about. Gravity isn't just a simple force pulling objects down. It has hidden variables that can affect how fast things fall. For instance, if you drop a feather and a metal ball in a vacuum, they will hit the ground at the same time. But outside a vacuum, air resistance plays a significant role, making the feather fall slower than the ball. This happens because of tiny frictional forces between molecules that we usually ignore. Most people spend years trying to perfect their physics experiments by eliminating errors, but fail to see how much these hidden variables can skew results. But now you know the real reason why your experiments sometimes don't work as expected, and it changes everything. Subscribe so the next one finds you.